Good day, dear viewers. My name is Steven Nueva, and I will present you today a study from Mark Martinez Sepulveda, Joan Marti, Marta Lopez Saavedra, entitled VOLCANBOX is software platform for volcanic hazard assessment. This is the overview of the presentation. Let's first start with the purpose of the study, which is to introduce and describe VOLCANBOX, a newly developed software platform designed to enhance and streamline the process of volcanic hazard assessment. Now for the objectives, which is to define, describe the key features, illustrate potential applications, discuss the benefits, and identify the target users of VolcanBox. And proceeding to the requirements, VolcanBox application integrates all the tools required to carry out the different steps of the aforementioned methodology. The key requirements are as follows: multi-platform, light, independent, compatible, scalable, and user-friendly. As you can see in this figure, this is the workflow and integration of spatial, temporal, eruptive scenario, vulnerability, and cost-benefit analysis in volcanic risk assessment. The second figure shows the compatibility and support issues in using different GIS software versions and plugins. And in this third figure, this is the main interface of VolcanBox displaying the available categories and tools for volcanic risk assessment. Proceed to the architecture, in this part, this will explain the high-level design and structure of the software system. Starting with the front end, the front end architecture of VolcanBox utilizes Electron Angular to handle all user interaction. This provides a customizable browser for creating desktop applications for web code with relatively low conversion effort. And then for the Angular model view model pattern, this promotes code reusability, well-structured and maintainable code, clear separation of GUI and logic, and consistent presentation across platforms, facilitating scalability. Next is the backend. The backend of VolcanBox is implemented in Python due to its versatility, high-level nature, simple syntax, strong presence in data science and machine learning, and large developer community. This architecture facilitates computational scalability by allowing work distribution across machine resources and is particularly advantageous for a future-oriented version, enabling easy distribution and load balancing of microservices across remote web servers, requiring only the backend to run and front-end to be served via web browsers. As you can see in this video, it shows the software architecture, which provides a general view of the different technologies and libraries that have been used and how they are distributed on a design scale. Proceeding to the internal design communication, the front end uses RxJS and the back end utilizes the Plus RESTful package. As you can see, and in this figure, you can see the sequence diagram showing the process of starting a simulation and updating progress and the players in VolcanBox. In this figure, you can see the sequence diagram showing the workflow of simulation raster data processing and map layer generation in VolcanBox. Now for the internal design, back for the GIS. Uh, the, the first one is the backend as map server, the front end for map display, followed by on-demand tile loading, then interactive visualization, and the utilization of OSGEO Python package, which includes GBAL, OGR, and PROJ libraries. Uh, the last one is the modularity and scalability, which allows changes to the front end and back end independently. And in this figure, it shows the sequence diagram showing the workflow from setting up the main VM to generating and serving tiles in VolcanBox. And the processing stage in VolcanBox leverages the computational power and extensive libraries of Python. And then after the backend receives the input data, it utilizes libraries like SciPy and NumPy to perform the necessary calculations for nested experiments. The, the results are stored, and if visualization is needed, the GBAL2 tiles library converts the data into map tiles. These tiles are then served by the backend map server microservice to the front end for graphical representation. Now, for the dependency management and isolation, this is that the Python backend and Electron Angular front-end package all their required dependencies within the application. For the informational structure, when a project is created, its metadata and a master digital elevation model defining the study areas terrain are stored. Each project has a .vbx file, JSON format in its root directory for metadata. Projects can be grouped into volcanic zones based on the geographic location, and, and then input parameters and results are saved as datasets within the metadata in .json files and associated with vector raster layers in dedicated subfolders. All sections can access project metadata and the main DEM. Data generated by one section can be accessed and used by others, promoting transversality. And in this figure, you can see a map showing a volcanic zone example that contains the location of various volcanic monitoring and research projects in the Canary Islands. And in the next figure, you can see the diagram showing the data structure and organization within the VolcanBox projects, including metadata, datasets, and result layer. In this next figure, it is the conceptual diagram of VolcanBox project showing the integration of geographic information, temporal and spatial analysis, simulation models, and hazard analysis. The next is the structure of the application and tools. In this part, the support tools enable experts to create and visualize geospace data, define metadata, and manage projects. And the next part, which is the statistical analysis, long-term and short-term. In this part, its purpose is to analyze how the volcanic system has behaved in the past and to forecast possible changes in it, as well as to identify most of the probable hazards and their location and possible extent in the future eruptions. The statistical analysis is divided into two modules: spatial analysis and temporal analysis. First, this is a screenshot of the VolcanBox user interface showing the main metadata section and hazard information for the El Hierro project. The spatial analysis. This focuses on the prediction of the location of future volcanic vents. It integrates geographical data with vector layers and representing various volcanic features. The core of this analysis is to calculate volcanic susceptibility, which often use Poisson process. VolcanBox implementation of spatial analysis based on the QVAS plugin have been rewritten in Python using NumPy for improved performance and independence from QGIS. The module includes for generating single density maps for individual structural elements and susceptibility maps that combine this based on expert defined weights. See in this figure, this is the probability density function of El Hierro project. While this next figure shows the susceptibility map section interface. Now proceeding to the temporal analysis, which is about it complements spatial analysis by examining the timing of past eruption to identify temporal patterns. It uses hazard assessment event tree application. The module offers long-term analysis using historical and geological records. Hazards adopts long-term assessment with real-time monitoring data to forecast eruption probability, location, timing, and likely scenarios during volcanic unrest. It allows for comparison between unrest episodes and features a dashboard for visualizing multiple monitoring parameters simultaneously. Both long-term and short-term tools have been reprogrammed in Python with real-time results displays and integration within the VolcanBox framework. In this video, you can see the asset long-term section interface in VolcanBox. And this one is the asset short-term section in VolcanBox, which is also showing real-time data analysis and indicators for El Hierro project. This figure, you can see the lava flow section interface. Here is the fallout section interface. Here is the screenshot of pyroclastic density current section interface and the lahar section interface, which is all by LVR project. Proceeding to the hazard maps, where the it discusses the hazard maps in VOLCANBOX that are generated by combining the results of simultaneous simulation models with spatial and temporal analysis. The shapebox tool facilitates the selection of event locations, either single points or areas based on susceptibility maps, to drive the simulations. It offers the widely accessible .aml format for visualization in Google Earth, acknowledging that 3D representation can sometimes be more effective for public understanding than traditional 2D maps. And in this video, you can see the shapebox tool interface in VOLCANBOX. Proceeding to the risk analysis tools, which is the volcanic risk coefficient that provides a graphical representation using factors like VEI, eruption rate, and potentially affected population. And then BADEMO or BADEMO, which is just about the cost benefits analysis tool. Volcan Dam, which estimates expected damage from volcanic eruptions. And in this part, the risk analysis tools are designed to be expandable with the current inclusion of these three tools developed by authors and collaborators and the potential for seamless integration of other relevant open use applications in the future. And as you can see in this figure, is this the cost-benefit conceptual diagram of section interface for VOLCANBOX. Now for the early warning tool. This early warning section to respond to volcanic alerts features three main tools: monitoring tool, alert tool, early warning system tool. This module interface facilitates continuous monitoring and short-term evaluation. You can see in this figure, VEWS conceptual diagram of section interface for VOLCANBOX. Now for the communication of scientific information, which emphasizes the importance of clear and effective communication of volcanic hazard assessments and forecasts. Opted to use the term forecasting rather than predicting. VOLCANBOX in this part, VOLCANBOX aims to simplify the visualization of uncertainty in both long and short-term assessments and provides recommendations for tailored communication strategies. VOLCANBOX quantitative data on eruption scenarios is intended to help scientists quantify uncertainty and provide clear forecasts to decision makers. For the discussion and conclusions, development and purpose of VOLCANBOX as a novel software platform aimed at advancing the field of volcanic hazard assessment and risk analysis. The authors position VOLCANBOX as a solution to the recognized disconnect between scientific methodologies and the practical needs of community planners and emergency responders. By integrating a suite of well-established tools within a multi-platform, durable, and user-friendly environment, VOLCANBOX facilitates as a more systematic, efficient approach to long-term hazard evaluation and short-term crisis management. Software streamlines certain processes, but it is intended to replace expert knowledge. Instead, it serves as a powerful tool that requires and relies upon the informed decision of volcanologists throughout the assessment and communication process. The genesis of VOLCANBOX, rooted in the collaborative research with the civil protection agencies, underscores its design as a means of translate complex scientific findings into accessible information for effective decision making and ultimately contribute to the tangible reduction in volcanic risk.